Good morning all. This is a third part of my video lecture on NMR spectroscopy. Today's topic is spin-spin splitting. Consider the NMR spectra of the compound chloroethane CH3, CH2, Cl. The NMR spectra is, first of all, we get peak for the maximum d-shielded proton. Here, because of the presence of the chlorine atom, the CH2 proton is maximum d-shielded and give peak at a lower magnetic field. Therefore, this is the peak for CH2 proton. And then we get peak for CH3 proton, and finally we have the peak for TMS. CH2, CH3, TMS. So we cannot count the peak for TMS signal when we are saying about the number of signals. Here the total number of signals is equal to 2, and the number of signal shows how many different kind of protons are present. Okay. And second is the location of the signal. Location of the signal shows how shielded or de-shielded the proton is. Okay. The position of CH2 proton comes first. That means CH2 proton is maximum de-shielded. And CH3 proton is near to TMS. That means CH3 proton is maximum shielded. So from the position of the signal, we can say which proton is maximum shielded or de-shielded. Okay. Then the intensity of the signal. The signal for CH3 is more intense when compared to that of CH2, because as the number of protons increases, the intensity of the signal also increases. Thus, the intensity of the signal shows the number of protons of that type. And the last point is the splitting of a signal. This is a simple NMR spectra. Then there is NMR spectra based on spin-spin splitting. The splitting of signal shows the number of protons on adjacent carbon atom. For example, the same compound, the NMR spectra of the compound based on spin-spin splitting is, here the compound first signal is of CH2. CH2 signal, CH2 give peak, or we can say the CH2 protons generate a magnetic field because protons are charged particles. Similarly, CH3 protons also generate a magnetic field. So there is interaction between the magnetic field of these two set of protons with the magnetic field of the external magnetic field. So because of the lateral interaction of the magnetic field of the two set of protons, there is splitting of each signal. The CH3 proton cause splitting of this CH2 proton. Similarly, the CH2 proton cause the CH3 signal to split. Thus, splitting of the NMR signal due to the interaction between protons on adjacent atom is referred to as spin-spin splitting. The splitting is actually into one more peak than the number of hydrogens on the adjacent carbon atom. For example, the CH3 signal split into 3. That means adjacent to the CH3 there are two protons, and these two protons cause the CH3 signal to split into 2 plus 1. Actually, splitting is based on n plus 1 rule, where n is the number of protons on adjacent carbon. Similarly, the CH2 proton split into 3 plus 1 is equal to 4. Because the adjacent to the CH2, there is CH3, contain 3 proton. According to n plus 1 rule, the CH2 proton cause splitting, or the CH2 proton split into 3 plus 1 is equal to 4 signal. Okay, and then the intensity of the splitted proton can be decided by Pascal's triangle. The relative intensities of the splitted proton is based on the binomial distribution given by Pascal's triangle. What is Pascal's triangle? Start with 1, 1, 1, 1, 1 plus 1, 2, 1, 1, 2 plus 1, 3, 2 plus 1, 3, 1, 1, 1, 3 plus 1, 4, 3 plus 3, 6, 3 plus 1, 4, 1, 1, 5, 6 plus 4, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. So this is Pascal's triangle. So if a signal split into 2, the intensity ratio will be 1:1. So if a signal split into 3, we get a triplet. This is of doublet. Split into 3, then the intensity ratio is 1:2:1. If a signal split into a quadret, then the intensity ratio will be 1:3:3:1. If a signal split into a pentet, then the ratio will be 1:4:6:4:1. So thus it can be split into hextet, heptet, like that. The signal can be split because of the magnetic interaction of the protons on adjacent carbon atom. So let's see the NMR spectra of the compound chloroethane based on spin-spin splitting. The compound is CH3, CH2, Cl. The NMR spectra is, first of all, we have peak for CH2 proton because that is the maximum d-shielded proton, and CH2 adjacent to the CH2 we have 3 proton. Therefore the CH2 signal split into 3 plus 1 is equal to 4, and if a signal split into 4, then the intensity ratio will be 1:3:3:1. It can be drawn as 1:3:3:1. Then we have signal for CH3. Adjacent to the CH3 there are only 2 protons. Therefore that split into 2 plus 1 is equal to 3. If a signal split into 3, then according to Pascal's triangle, then its intensity ratio is 1:2:1. So the nature of the signal 1:2:1. And finally we get signal for TMS. This is a signal for CH2, signal for CH3, and for TMS. This is the NMR spectra of the compound CH3, CH2, Cl based on spin-spin splitting. Thus a signal can be split into multiplets because of the, what is the reason? Here there is a magnetic field generated by these CH3 protons. magnetic field can be generated by CH2 proton also. These magnetic moments interact with the magnetic field of the external radio frequency radiation, and that causes splitting of the signal into multiplets. So let's see another example. CH3, CH2, CH2, Cl. Chloropropane. So first of all, let's see the simple NMR spectra of the compound. B0. The compound contain how many set of protons? Compound contain 3 different set of protons. What are they? 1, 2, 3. Because the two CH2 are not equivalent, because this CH2 is attached with an electronegative atom, and this is the maximum. This is having maximum d-shielded proton. Okay. Therefore, this gives signal at a lower magnetic field, or we can say this gives signal downfield. This side peak is called downfield peak. Here the peak is called upfield, because that gives peak at a maximum magnetic field. Okay. So CH2 gives signal at a lower magnetic field, CH2Cl, CH2Cl. Then we get peak for the second CH2. And finally we have the peak for CH3. This is the NMR spectra of the compound. Now let's see the NMR spectra of the compound based on spin-spin splitting. First of all, we have peak for CH2Cl. CH2Cl, this gives peak initially. Okay. Adjacent to this CH2Cl, there are only 2 protons. Therefore, the CH2Cl signal, that proton signal split into 2 plus 1 is equal to 3. If a signal split into 3, then the intensity ratio based on Pascal's triangle is 1:2:1. This is a signal for CH2Cl. Next, we have the signal for the middle CH2, and the middle CH2, adjacent to middle CH2, there are 3 plus 2, 5 protons are there. The middle CH2 signal split into 5 plus 1 is equal to 6, according to Pascal's triangle, or by n plus 1 rule. If a signal split into 6, it is called hextet, and the intensity ratio is 1:10:10:5:5:1 based on Pascal's triangle. So the CH2 signal, the middle CH2 signal can be drawn as 1:, let this be the approximately 5th fold, 5:10:5:1. And finally we have the signal for CH3 proton, and adjacent to CH3, adjacent to the CH3, there are only 2 protons, CH2 proton. 2 plus 1 is equal to again 3, and if it is 3, the intensity ratio is 1:2:1, and the signal for CH3 is 1:2:1, and this is of TMS. This is signal for CH3, and this is signal for the middle CH2, and initially we have signal for the CH2Cl. So this is the NMR spectra of the compound CH3, CH2, CH2Cl based on spin-spin splitting. Let's see another example. Let it be 2-chloropropane. This is a compound. The simple NMR spectra. First of all, we get peak for the middle CH group, and then we have two CH3 group. The two CH3 groups are equivalent. Therefore, we get only one signal for the two CH3 groups, and its intensity will be very high because it contains 6 equivalent protons on TMS. CH3, TMS. This is the simple NMR spectra of the compound. And let's see the NMR spectra of the same compound based on spin-spin splitting. So first peak is of CH proton. Adjacent to the CH proton, how many protons are there? Adjacent to the CH proton, there are 6 protons. According to n+1 rule, the CH proton split into 6 plus 1 is equal to 7. If it split into 7, then the intensity ratio will be 1:6:15:20:15:6:1. So we have to draw the NMR spectra of the CH peak based on spin-spin splitting as 1:6:15:20:15:6:1. 15:6:1. And next we have peak for CH3. Adjacent to CH3 there is only one proton. One proton split the CH3 signal into 2. If there are splitting into 2, then the intensity ratio will be 1:1. Therefore, the signal is a doublet 1:1. And then we have signal for TMS. This is the signal for CH proton, and this is the signal for CH3 proton. This is of TMS. This is the NMR spectra of the compound 2-chloropropane. Okay, so 2-chloropropane give 2 peaks in the NMR spectra, and from spin splitting we can predict the number of protons on each carbon, and thus we can very easily identify the structure of an organic compound. So suppose we get the NMR spectra of the compound as like this. If we have the NMR spectra of the compound, we can see that here the signal split into 1, 2, 3, 4, 5, 6, 7. That means adjacent to this carbon there are 6 protons. Okay. Similarly, the CH3 signal split into 2. That means the adjacent to CH3 proton, carbon possesses only 1 proton. So from this, and we have only 2 signals in the NMR spectra. So from these data we can find out the structure of the compound. So NMR spectra is a very powerful tool to identify the structure of an organic compound. Very easily we can predict the number of protons present, number of proton along with each carbon atom, position of each signal. All these can be very easily predicted by the NMR spectra of a compound, and so we can say NMR spectra is a very powerful technique for the structure elucidation of an organic compound or for the qualitative analysis of a compound. Okay, then the most important application of NMR is MRI scanning, magnetic resonance imaging. It's a very powerful medical imaging technique to visualize the internal structures of body in detail. So MRI make use of the property of NMR to image nuclei of atoms inside the body. So what we are doing is we are placed inside the powerful magnet of the MRI instrument, and a body contains a lot of water molecule. Water contains protons, and when a magnetic field is given, all these protons present in our body tissue are aligned in the magnetic field. When a person is kept inside the powerful magnetic field of the MRI scanner, then the radio frequency radiation is used in NMR. So radio frequency radiation is turned on. So radio waves of the right frequency, known as resonance frequency, interact with the precessional frequency of our body protons, and if there is resonance, then there is flipping of proton. Then what we are doing is we are turning off the radio frequency radiation. So when the electromagnetic field is turned off, spin of the proton relaxes or returns. The process is called relaxation, and signal is generated from our body, and these signals are converted into images, and from the image we can very easily identify, the doctors can identify if there is any deformity. So MRI make use of the principle of NMR. So we are kept inside the magnetic field and radio frequency radiation is used, and from the water of our body tissue the protons aligned, and there is flipping of proton, and there is relaxation. When the NMR or the radio frequency radiation is cut off, there is a process of relaxation, and this relaxation is converted into signal, and that signal is obtained as an image in the instrument, and from this image we can find out the deformity present. Thus MRI make use of the principle of NMR. Thank you.